people online, welcome to everybody here. Just going to be really quick, very efficient, just like C++. Not going to talk very long. I just want to say a few thanks to the people who helped make this possible. That's, of course, the people in the back, the Channel 9 team streaming live, Denise Begley, who made all the logistics possible. And what we're going to do is invite Herb Sutter up here in about 20 seconds. He's going to make a very special announcement. So I just wanted to say, again, thank you, welcome, and Herb, come up here, man.
Thank you, Charles, and thank you, everybody, for coming, and all those who are watching. Even in the room, we have folks from 18 countries, 23 states in the United States, and a worldwide audience, so thank you for attending. And before I invite our most distinguished and most important speaker, we wanted to dedicate this conference to a very important gentleman. So if we could have his picture on the screen, please. We'd like to dedicate this to one of the most influential computer scientists in our young industry's history. There are very few people on the face of the planet who have made as great a contribution, and he's also the reason why we're here today. When we think about what happened at Bell Labs, where Bjarne and AT&T and C++ also grew up, before there was C with classes, before there was C++, there was C, the most influential programming language in the world. Every single modern language owes a debt to it and is either directly derived from it or borrows heavily from it and has been influenced in all the coding we do by what this man did 40 years ago. Now, he was also famous for another thing, the Unix operating system, together with Ken Thompson, which has, again, directly influenced or actually directly led to almost every major operating system in use today in mainstream. That's a very big set of shoulders. So we appreciate very much his contribution, and we think of all the awards that RAII has received. It's because, coming back to C, it is such an empowering part of native code. It is what has made our industry possible, because libraries that are portable, that are efficient, are what this world is built on. This world runs on C and C++. It is the foundation of everything, including the managed languages. It is what we all build on. And so we'd like to dedicate this event to the memory of the recently passed Dennis Ritchie, the creator of C, co-creator of Unix, to whom we all, and everybody who uses software on this planet, owes a great debt. So with that, we'd like to dedicate that. And I'd like now to introduce our keynote speaker. Bjarne Stroustrup needs no introduction. He's the creator of C++ and a friend of Dennis Ritchie. And we would like now to see C++ 11 style, a touch of class. Bjarne.
Thank you. Yes, thank you very much. Dennis is much missed. He was a real gentleman, and when I talk about memory model issues, that's borrowed straight from C, and that's a very important part of C++. Okay, so I have to talk about the future, and I'm going to talk about the issue of style. How do you write code, and how do you write code so it's maintainable, performing, all of these good things. When I come into a room, especially one of these virtual rooms on the web, I seem to be the only one who doesn't quite know what C++ is. Everybody has some kind of simple explanation that fits their view of it, and you see a few of them there. And the effect is like the blind man and the elephant. If you have only seen the tail of the elephant, you know what it's like. If you've only seen a leg, you know what it's like. I try to look at the whole elephant, and I try to characterize it, but it's hard. There's many bits to the elephant. They're all essential for the elephant, but it's hard to be simple about what it is. So here's my sort of trying to characterize what C++ is particularly good at, and particularly aimed at. It takes off from C, and systems programming. But where it really matters, where it makes a difference, is in the area of infrastructure. That is, where you build something that other things build on, that people rely on, where you have resource constraints. This can be a cell phone, it can be a Google-style lookup. You're constrained by various resources, and you have to have reliability and dependability and performance. That kind of application, it can be infrastructure or it can be applications that has a similar kind of constraints, is where C++ shines. I've tried to come up with a buzzword, but I'm not very good at it. Lightweight abstraction programming language is accurate, but it's probably not good marketing speech. So let's go on. One thing that I think it's important to realize when you talk about programming is that no one size fits all. I always hear these things like, what is the programming language? What's the dominant programming language? What's the future programming language? Which is the best programming language? Best programming language? Who for? For what? There's no reason to believe that there's one language that's best for everything, and I don't think there is. And so I'm trying to characterize what C++ is good for, where it fits. There's things I would probably use JavaScript or Python for, but I probably wouldn't use them for, say, the JavaScript interpreter. That's C++ domain. Anyway, so different applications have different constraints. You worry about hardware resources, reliability, efficiency constraint. It varies. A lot of applications can crash. It doesn't hurt anybody. The extremes are where all that matters is to get to the market fast. That's not C++'s core domain. There are, however, places in the other extreme. If the program fails, people die. It's always uncomfortable if your tools are used in such an area, but somebody has to do it. And there's a simple fact that 50%, I mean, if you double the overhead of something working on a server farm, well, you need at least another server farm, and probably two because of the communication. So that's the areas where C++ shines. Over the years, we've tried to say what we're doing with C++ with many words. I mean, people want true object-oriented style. I've never been on that team. There's nothing that says everything fits in a hierarchy. And as a matter of fact, it doesn't. Other people say, well, C is perfect, and you just need a few details. Well, if you write C with void, stars, and macros and casts, you get C-style bugs. And you see all of this in the C++ world and the C++ code, and we've tried to say multi-paradigm, but that doesn't actually capture anything. They were never meant to be separate ways of programming. They were meant to take part of a synthesis that is C++. And so we can think about what we really want. We want something that's easy to understand for humans and tools. We want something that's correct, maintainable. Modularity is good. Interfaces are absolutely essential in modern software. We want to have effective resource management. We don't want to leak memory. We don't want to leak locks. We don't want to leak files, etc., etc. That's a big issue. Today's world tends to be multi-threaded, concurrent, so we want to be able to do thread safety without losing all the other advantages. Efficiency we want in many, many applications. It seems to be getting more critical in critical areas, cell phone and sort of web server kind of things are the extremes, but also some high performance numerical stuff. And portability, except when there's reasons not to, because next year's model, next year's operating system is going to be different. If you don't want to port to anything else, at least you want to port to your future hardware. And that's not going to be the same. So that's what we want. That's hard to get. I picked Don Quixote here from this slide for that reason, because sometimes it feels like an impossible task. But we're making progress. We've made steady progress over many years, and now we're actually better than what we used to be by a large measure. So we're looking for a synthesis, integrated set of language features, and C++ is a step in that direction. And then we need an articulated guideline for how to use it. If we just use the new features just as features, we're wasting time. And if we don't use them, well, we're getting the old stuff. We need to use a new set of features, new set of techniques to gain what we really want: dependable, well-performing, maintainable software. And it's those guidelines I refer to when I talk about style. So here's an overview. First, I'll give you an example of what I think is ghastly and I would like to do without. Then I'm going to talk about the various aspects of this stuff. And there's a paper that I wrote. This one doesn't work over there on the screen, but you can see that paper, Software Structure for Infrastructure, Software Development for Infrastructure. That's a paper I wrote at the same time as I was writing this talk, so there's a great overlap in the examples. There's not a written version of this talk, but if you read that paper, you'll do fine. It's in this. It's a key paper in this month's IEEE Computer. So I'm going to talk about C++ 11, but not really about the language features. I'm going to talk about how to use it well. And this is part of a long-term project to figure out how to use C++ well, how to figure out how to blend the language features into coherent style. And I'm not going to talk about the individual features except when I absolutely have to. If you want to have a feature-by-feature explanation of C++ 11, which was approved last year, there's a picture of the committee in Spain cheering after the final vote. Then you can go to my C++ 11 FAQ, and there's feature, 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 feature. And if that's your view of the world, that's fine. That's where you look. I'm trying to see how to blend it. Most of this is shipping. This is not a science fiction talk. No compiler ships every detail, but all the major compilers ship important parts of the of C++ 11, so you can experiment with it. You can actually use some of it in shipping code. And the standard library is shipping basically complete. So here is some piece of code that I think is pretty ugly. And it's asking for inefficiencies and asking for errors. This happens to be QSort. Very common, very popular, 19 sort of early 70s kind of function. It sorts memory. You have to give the number of bytes of elements. You have to write an element comparison function and pass it. If you have to explain this to a novice, you're probably in trouble. Like, I have some calls of QSort there, and I have to give the number of elements. I mean, why doesn't the array know its number of elements? Why does an array of double doesn't know the size of a double? Well, and why does the language not know how to compare doubles? The point is that we have carefully thrown away all the useful information that could have answered those questions, and we're dealing with memories, a number of bytes in memory, and that's just throwing away. You have to use an inefficient indirect function call that prevents inlining, just to make sure that things are slow, and you have many opportunities for writing more code and for writing bugs. And if you look at the implementation of QSort, it's pretty ghastly. I looked at the web, and out of about 20 versions of QSort that I found, I would say 18 was educational frauds. They were simplified so that they were easier to understand, and in the process of simplification, they became totally unrealistic. They could compare integers, for instance, but if you look at it, swap swaps bytes. It only works for plain old data. If you have a higher level data structure, it doesn't work. Furthermore, swapping element byte for byte is just not a good idea. It's slow. A lot of indirect function calls, again, slows things down. This is what I would like to get away from. It's far too much code. It's far too error-prone. It's far too hard to maintain. It's far too hard to maintain efficiently when hardware change. And is this an unfair example? I don't think so. I didn't make it up. It's been used in education for decades to teach new programmers how to write code. And the style is not uncommon in production code. I wish it were, but it isn't. And I've seen worse, much, much worse than this. What I showed you was quality shipping code of that style. The amateurs do much worse. And the students aim for this level of code. They feel great when they write this code. They are convinced they're writing efficient, good code. It's cool. They think it's cool, and their idols did it. Maybe their idols did it back when there was nothing else you could do, but still, this is the kind of code that bright students aim to write. This is sad. And it's not just a C, C++ style issue. It happens in other languages, but I see it more in C and C-style C++. So that's a problem. I'm talking about C++ and using C++. So this is what I like to get away from. And it matters. I think it's the bad use, the inefficient use of C++ is one of the worst problems. The good news is that makes progress relatively easy. You don't need any new compilers, new language features. On the other hand, bad code breeds more bad code. People imitate what there is. People think that if it's that ugly, it must be that ugly for a reason, and therefore it must be good. Or this is our house style. New things, different things must be dangerous and bad and definitely inefficient. That's the kind of sick logic you see. And many are self-taught. They take books that were written decades ago. They ask other novices that doesn't know either. And, well, the problem is bad. So what do I want instead? I mean, it's easy enough to criticize, but let's put something instead. I want simple interfaces. If I want to sort a container, I want to declare sort of a container. Can't quite do that yet, but we're close. I can get simple calls. You have a container that's a vector of strings. You can say sort of the vector of strings. We can do that now. That's all right. And we can get uncompromised performance out of that. That sort runs faster than qsort by a large margin. I'll get back to that. But the reason it beats it by, qsort by a large margin is it doesn't throw away all that nice, useful information we just gave it. And we would like to write code without breaking the static type system. We can do that. Just stay out of the dark corners where you make type errors. And resource leaks, well, you don't have to leak resources. That's old style code. And I don't mean plug in a garbage collector. I just mean don't leak. I'm not saying it's trivial in all areas, but major progress has been done. So I'm going to talk about type-rich programs. These sort of intermediate slides with big pictures are just to give me a chance to breathe and think about coming next and notice that there's a break in the performance. So I'm going to talk about type-rich programming. And when I talk about interfaces, I mean interfaces that are not just strongly typed in the traditional sense, but actually typed with meaningful types. So if you look at the first set of examples up there, increase speed with a double. Double? What does that mean? Is it meters per second? Is it miles per hour? What does that double mean? I want to draw an object. What's an object? There's no information in an object. Can I draw an object that that happens to be a Fourier transform? I don't know. And there's an example of a rectangle. Give the rectangle 4 integers. What does that mean? What do those 4 integers mean? Are they 2 points? Are they a point and a height and a width? What are they? I mean, these kind of examples are pervasive in software, and they're interfaces, they're checked, but they don't check very much. They are basically free of semantics. So what I'm recommending is a style where if you increase the speed, give it a speed, which is a type that so that you can't throw in any old meaningless floating point number. If we want to draw shapes, let's say we draw shapes, not objects. It's sort of an extremely overly general thing where sort of anything can be an object, so I've said nothing. And for the rectangle, I can say what I mean. A point and a point, or a point and a box. An area outline. And notice that the minute you start saying what you really mean, you can have different versions, as I have for rectangle here. One of the most effective ways of controlling your thinking, controlling your code so that you don't make mistakes is units. We all talked about units in high school. Here, a speed is something that's meters per second. It's not meters per second squares. It's not a no unit thing divided by seconds. And an acceleration is a speed divided by some seconds. People have again and again designed systems for writing such code to save them from errors, to do what they learned in high school. But they are not used in the real world. In particular, that's the Mars Climate Orbiter. It tried to land on Mars a few years ago. Unfortunately, it was about 150 miles off course at the time, and that was the end of that. That's a $560 million gadget. It's the equivalent of the lifetime's work of 200 good engineers down the drain, or in this case down to Mars, because somebody didn't calculate with units. Imperial measures here, MKS system, SI system here, a constant move from the one world to the other through one of those double interfaces, and it changed its meaning by a factor of 4.5 in that process, and this one went down. So why are people not doing this? Because languages don't support them except for specialized languages. And you can't use specialized languages all the time because you have to invent a new one for each special application. You could do what is on that slide at runtime, but at runtime you have to store the values, and then you have to compute the correct answer. And when you do that, you've doubled your memory requirements, you've doubled your compute requirements, and on spaceships at least, there's two things you have a constant shortage of, and one is memory, and the other one is compute speed. So the engineers decided, like everybody else in their situation, that they would just keep track of the units and get it right. And in this particular case, fortunately a rare case, they blew it. So let's see what we can do. In C++, we can actually write with units if we go and define units and then use them. So the basic idea of a lot of C++ is that you build your own types and then you use them, as opposed to trying to write in a basically low-level language. So here I'm saying that first I want some units. And units are in the MKS system, the subset of the SI system, that can meters, kilograms, and seconds. And a value is something that has a magnitude, which is that double we were seeing before, and it has a unit. So you can be 2 meters per second, or you can be 3 kilograms, or something like that. And I can define speed as the unit that is meters divided by seconds. Still don't seem to work. And acceleration is meter divided by seconds squared. So you can write that, and then this code becomes standard C++. So the code, as would have been the textbook kind of version, would work. Now, the interesting thing is that we've been able to write what I just show you here on the slide for about 10 years, a bit longer than that. And libraries like that has been built. Particularly, there was a nice one from Fermilab that could do this. And people had to write it, and they had to write a notation like you saw there. And that was a downfall of those libraries. The physicists, the engineers just refused to write code like that. The very explicit version is unreadable. You start using shorthands, and very soon you get something that is thoroughly obscure. And basically, people didn't do it. So one of the things that we can do these days, at least when the compiler is shipped with the feature of user-defined literals in all the compilers, is you can define your own literals. So you have a second squared, and you can define operators, these operator literals, that says if you give a long double suffix by an S, you make it into a second. You make a long double suffix with S2. It's second squared. And now that code, like we took out of the textbook, will actually work. And this is essentially free. It's a compile time computation. It's a simple compile time computation, so it's not going to slow you down. There's no fancy trickery in that code. And there's no runtime overhead. It's the same number of bytes. It's the same number of cycles that is displayed. So we can now afford to have the checking that we knew we should have done, but for the last few decades didn't do, and sometimes lost big. So this is an example of what I call type-rich programming, and I'm recommending that interfaces should be strongly typed, but not just with random type, but with meaningful types. Assign types that has a meaning, has a semantic, not just doubles and integers or objects. They don't tell you anything. The next thing that's part of what I think is good style, and I recommend, is be careful dealing with resources and errors in a considered and systematic way. So here's an example of sort of fairly standard code. It looks all right. I open a file and I close it. The problem is it's naive. And this is a fairly common source of bugs. That use F there, if it's only one line, it's probably fine. But in a real program, the code that's actually done to use F may be a couple of pages, and it may be split over several functions. And it's fairly easy to forget to get to the F close. After all, there might be a return statement in there, there might be a C long jump, or there might be an exception, and you never get to the bottom that closes F. So everybody that's looked at this decided, oh dear, we have to do something about it, and we do something to deal with exceptions. Now, if you report errors as exceptions, you need exception handling. And so people write something like this. There's a try block there, and we catch all exceptions, close the file, and everything's fine. You can invent a better syntax for this if you like, but it doesn't change. A better syntax will not change the fact that when you are acquiring a resource, you have to remember that you're acquiring a resource, and then catch the exceptions that might be there and release it. Okay, this is very ugly code. There's a lot of it, and it's more complicated than what I started out with. I mean, why would I expect code when this was error prone? Why would I expect this to have fewer errors? Bugs correlate with complication and with size of code. So we would expect there to be more bugs there in real life code. So that's not good. And the reason for the whole problem seems to be that I keep talking about a resource, right? Do you see any resources there? I see 2 function calls. They happen to be well-known functions, so I know that if I do an fopen, I should do an fclose. The manual says so. The compiler doesn't read manuals. A lot of programmers don't read manuals. And in a lot of resources, it's not one we know as a maintenance programmer or such. So I think the idea is to represent your resources directly and get rid of that mess there. And so here's the example. We write a file handle. A file handle is an object that owns a file handle. And you create one of these file handle objects by giving it the name of the file and the open mode, and it opens the file. If it can't, it throws an exception. And the destructor for that file handle releases the resource. And now I can simplify my user code, saying, well, here's the file handle, and then use it. And at the end, whenever we exit that block, with an exception or with a return, the destructor is called and it releases the resource, in this case closes the file. That's the resource acquisition is initialization idiom, which is probably the best example of why I shouldn't be in marketing. Anyway, I didn't have a good day when I named that, and naming is not one of my strong points. So for all resources, we can use RAII to keep track of the simple uses of resources, which are by far the most common examples. So in the standard library, we do it for strings, we do it for vector, we use it for maps, which keeps track of the data, the elements that is allocated there. We do it for locks, we use it for file streams, we use it for thread handles. It's deep into our standard library architecture. And so here there's an example, there's a mutex and there's some shared data, a very simplified example. And then I grab the lock, manipulate the shared data, and when I get out of that, the lock is released. One would think that you couldn't mess up with a simple lock, unlock. But again, if you know that the lock and a lock operation takes a lock and have to remember to get it out again, you will probably get it right. But in general, people can forget. So we try to have anything that considered a resource owned by some kind of local handle. But let's see what people actually write. So here is sort of a classic piece of code. You make a new gadget and you assign it to, well, it should have been a gadget pointer. And at the end, we delete it. Even if there wasn't a typo on this slide, it would leak like mad. Fortunately, the compiler will stop that one, but the compiler doesn't work on my slides. So imagine that P is a gadget pointer. So there's several ways of leaking, like returning or throwing an exception, so we never get to the delete P. It's exactly equivalent to the file open, file close example, and it's not actually uncommon. People use a lot of pointers, and the pointers are not safe against exceptions, so it leaks. And people start screaming for garbage collectors. My answer usually is, don't leak. Let's see, we could use a shared pointer which takes care of this problem. A shared pointer the destructor for the shared pointer will release the resource if you're leaving its scope, and if it's shared by others, the last destructor will destroy it. But look at this sample. I solved the leak problem, but why am I using a shared pointer? I'm not sharing anything with anybody. This is just just my, my local use of this. So we can use what's called a unique pointer, which simply keeps track of a pointer in a scope. So that's what you use if you just want exception safety and want to have a very efficient way of making sure that your pointers don't mess up your code. So this works, but why have any kind of pointer? I mean, I'm not passing around anything at all. So really we should go back to just grabbing the resource, using it, and let the destructor release it. And again, the resulting code is much simpler. It's also more efficient. So elegance and short code and performance tend to go hand in hand. So basically, the lesson I draw for this is that we should prefer classes where the resource management is part of their fundamental semantics. I mean, vector keeps track of elements. That's what vectors do. Threads keep track of some things in the runtime environment. That's their job. They know about stacks and various mappings and scheduling and things like that. I don't have to do it. It's their job. And so their resource management is embedded in the semantics of those types. So that's fine. And if you absolutely have to pass pointers around and such, you can pass unique pointers around when you're just transferring something. And you can use a shared pointer if you have shared ownership. My opinion is that you don't share as often as you think you do, and so you don't need it as often, but it's certainly better than just trying to keep track of it yourself. The reason I'm a little bit worried about unique pointer and shared pointer and prefer the objects themselves is that if you have two pointers to something, there has to be a protocol of who uses that object when. And so, as somebody else says, any pointer is a potential race condition. Who reads, who writes, not even with concurrency, but just in a program, when do you do the updates? There is a problem that tends to get people to use pointers or shared pointers and things like that. And that's basically how to get a lot of data out of a function. I mean, take a simple example. I want to add two matrices. And the way you usually do that is you take in two references. That's a very efficient way of getting to the elements of a matrix. The problem is, how do you get the resulting matrix out again? You have to make a new matrix and then get it out. One way you could think about is to pass out a pointer. But then you have to write code like that, and that's just too ugly to even think about. And anyway, if you did that, there will be a new inside the function, and who does the delete? Now you're getting yourself a memory management problem. And sooner or later you will start inventing use-counted pointers or garbage collection or something like that. That's not a good solution. Let's try something else. We can return a reference. At least it looks right. But again, the question is, who deletes that object? And people look at this and it says, what delete? I don't see any pointers. There's no pointers here. So there is a memory management problem that's hidden. That's even worse. So there's a lot of things that we can do this. We can just pass in the target that we fill. So the plus should take the two matrices and fill the third matrix that you pass in as a target. But now the normal notation of res equals a plus b will no longer work. Instead, we have to say operator plus of a comma b and res and allocate res. We're regressing into assembly code. Assembly code can be very efficient. It can be very logical, but you know, there's a lot of writing to be done. There's a lot of optimizations that can't be done automatically because, well, the programmer is supposed to do it himself. So let's see what we can do. I want to get the data cheaply out of the function. I want to write code like that I take things in by reference and I return a matrix. After all, what does matrix plus do? It creates a new matrix. And so I can write code like that. That's what I want. Now, the problem is that if, say, this was a 10,000 by 10,000 matrix, copying the matrix out is rather expensive. You don't want to do that, and people start thinking, how can we get it out without actually copying? And there's a couple of dirty tricks. You can have a result stack of matrices, and it becomes unmanageable. But finally, you just realized, I don't want to copy any matrix. I just want to move it out. I mean, we know this. Little babies can do this. Say there's a matrix, it's here. I want it over here. What do? Make a copy and destroy the original, or do this? I mean, babies can do it, so fine. I don't make a copy of this one, give the copy over there and destroy the original. There's something fundamentally wrong. That's the way computers tend to work, right? You make a copy of an integer. It means that's what machines do. But it's not what we want to do with matrices. We want to be able to move objects. If it's a real object, if it's a resource, we want to be able to move it. So this is the way we do this. Here is the matrix, add, and I make a local matrix inside it. I fill it with all the right information, and I return it. What I want is, instead of that to be a copy, I want it to be a move. That is, R points to some elements, and after the return statement, res should point to those elements, and the internal R should point to no element, so it goes away cheaply. That's what a move is, right? Simple as that. And in C++ OX, there's direct support for that way of writing code. I've been writing code like that for a decade, but it's a bit tricky. Now we have direct support. That funny-looking constructor there, matrix ref, is a move constructor. It does moves. And the way you implement a move is you copy the representation. That's what computers can do. And then you zero out. Set the original representation to be an empty matrix. And so you do that move trick. And again, this stuff is all over the standard library now. Vectors can move, lists can move, singly linked lists can move, maps, unordered mapped hash tables, all these good things we have now. They are basically resource handles. They are treated as resources. They can move. And so if you have code that copies things like that, it'll now run faster, which is good. But also, you can now write code that returns things like big vectors cheaply. You don't have to pretend you're an assembly coder and fill a target. You don't have to mess with memory management, such things. This is cheap. This is dirt cheap. If the matrix representation is a single pointer to the elements, as it often is, the cost of that move is 2 integer assignments or double assignments. That's cheap for parsing 1 million elements. Okay, so that was roughly what I was going to say here. The style lessons here are that naked pointers are dangerous. Pointers and array are splendid for dealing with hardware at the lowest level. They are not what we want to keep in our productive, maintainable code. So we keep naked pointers inside functions and classes that implements something that require them. And keep the array out of the interfaces, use containers instead. We know how to pass them both in and out, so we don't need to use pointers and arrays for that. Pointers and arrays are implementation level artifacts. We try to keep them out of it. You don't use pointers or functions to represent ownership. And one dead giveaway for people writing old-style code is the code littered with new and deletes. I mean, it's like code littered with malloc and free. I mean, if you write that level of code, what do you expect? Leaks. I mean, if you write C-style code, you expect C-style errors. So let's try and do something better. Return objects by value, as I said, because we can use by value. Now, One thing that's extremely important if you want performance out of fairly high-level code is to have reasonable data structures and algorithms. Here I'd like to show an example that first was shown to me by John Bentley of algorithms fame. Make a sequence of random integers, keeping them in order. And so you're given the numbers 5, 1, 4, 2, and it builds up the sequence as you see it there. And then you remove them again by giving a set of positions of which one you take out. And so the exercise is, for which n is it better to use a linked list than a vector or an array? And everybody gets this one wrong. Here's... My graph has disappeared. This is embarrassing. Okay. Okay. So, imagine this to be a graph. The imaginary low line down by the bottom showing efficient usage, little time, is the vector. The one that is looking like an exponential, trying to go through the ceiling, is the list. And trying to figure out why the list is so inefficient, I thought, maybe it's all this allocation that's being done for the nodes. So the little middle green line, which you can't see either, is the lists with allocation taken out, totally pre-allocated. The point here is that the vector is always better than the list, and the list gets worse the further you go out. And this is for the case where you're doing a lot of insertions and deletions, which, when I was taught about data structures, was what you use lists for, because they're really good at inserting, deleting. If you want to insert in the middle of 100,000 integer vector, you have to shove, on average, 50,000 elements one position. If you take one out, you have to shove them roughly half the way back. Now, this is completely irrelevant. What matters is the linear search to get to the insertion point. Of course, you have to go through half of the list to find on the average insertion point for a list. And in an attempt to fairness, I also did the same for vectors instead of using a binary search. But anyway, so the linear search dominates completely. And linear search for vectors, it's not actually such a good idea. First of all, a vector is, for a list is much bigger for a given data structure than a vector, because you don't have to just store the element, the integer. You have to store the 2 pointers forward and backwards. You have to use a doubly linked list if you're inserting, otherwise you have extra problems. And that completely dominates. So the graph here, this graph here that you can't see, shows you that there's not a minor disadvantage here. We're talking about things being 50 or 100 times slower with a linked list. And the traversal dominates. So compactness matters. Vectors are more compact than lists. And predictable usage patterns matters enormously. With a vector, you have to shove a lot of elements over, but caches are really, really good at that. So surprisingly, vectors are random access constructs, but you can stream them. Lists don't have random access, but when you traverse lists, you keep doing random access. There's a node here and it goes to that node in memory. So you're actually random accessing your memory and you're maximizing your cache misses, which is exactly the opposite of what you want. So the lesson I'm trying to say here is stay compact, stay predictable, and you have 3 orders of magnitude of performance to deal with here, to gain by being compact. Now, people have looked at that graph you didn't see and said, well, I don't use lists of 100,000 and 200,000 elements. And there's two kinds of people. There's sort of the Google and Amazon people that says, because I don't have such little data structures. And then there's the students that think 1,000 elements is a long list. And so I don't use that many 100,000 lists, but using a few 100,000 element lists is exactly the same. As a matter of fact, you can get the performance effects out of individual data structures. So here's a very simple one up there, a vector of points with 4 points. And the way that will be laid down in memory, if you use the standard, is up there labeled C++. You have a little handle. A lot in C++ is these little handles that tells you how to use things. And then the resource managed, which happens to be a compact data structure with 8 integers, because it's integer points. And that's fine. It's compact. You have a single dereference to get to it. You have a little bit of memory overhead because vector keeps its elements on the free store, so you get the extra word or two as a free store header. But that's the way it looks. It's fairly compact. If you don't want to put it on the free store, don't. But usually that you can afford it. Now, I'm told very often that I have to write in a truly object-oriented style. And there's languages that ensure you do that. And in a truly object-oriented style, of course, an object is referred to by a reference. So you have a reference to the object. There's the object down there in the next line with a 4 with a count in it. And this happens to be a container of user-defined objects. So again, you have a container of references, and there you have the objects. So that turns the linear compact data structure into a linked structure. We just saw on this invisible slide what linked structures do to your performance. And here you get a rough doubling of the size of the data structure, and whenever you want to access an element, instead of getting one indirection, you get 1, 2, 3 indirections. And indirections, again, is things that modern computers don't like very much. Pointers are poison to most optimizers. So you can get this again. So I recommend compact data structures and fairly regular access to them. That's the winner. Similarly, we have to simplify our control structures. Let's look at an example that some friends of mine presented me with. It was a very simple example. A lot of operating systems, a lot of GUIs have the operation for taking something out of a list. Think of it as say a menu, and move it over there. That's the operation. And a guy wrote a piece of code that solved this problem for a particular GUI system, and there was 25 lines of code. I mean, I just explained to you what we're doing in roughly one sentence. Take an element and put it over there. And there was one loop, there was 3 tests, and there were 14 function calls. Now, the author looked at this and says, well, you know, this is rather messy code. And even though he was a professional experienced programmer, or maybe because he was a professional experienced programmer, he worried that it might not be correct. I mean, 25 lines of code with loops and conditions, how will you know? And is it maintainable? And he decided it probably wasn't maintainable because he had to think about whether it was right or not. The next guy coming along would probably not think as hard and make a change. And is it usable elsewhere? No, it was just full of things that was very specific to that particular GUI. And the author, being a real professional, requested a review. Professionalism is very important, and is something we've got far too little of in our field. So The story I got was from the guy that came in to do the review, had requested. And they looked at it for a while, actually almost a whole day, and found that what the code really did was find the insertion point, and you can write that as a find algorithm from the standard library, and then it has to insert it. You have to move it into the point, and that's a rotation. So you can rotate from before the insertion point, or you can rotate from behind the insertion point, so you get that code. If you know the standard library, this looks fairly reasonable. If you don't know the standard library, there's a standard definition, and you can go in and find it and read it. It's well defined as opposed to the random code. And it is an algorithm. The only problem is, so it's maintainable, but it's a very special purpose. Vector wasn't the standard vector. It was the vector of GUI objects. And the coordinate was very specific to that library. So they looked at it a bit again and said, we can generalize this to any GUI. And they came up with that version, which is called Gather, which is shipped by in different versions by actually several libraries these days. And basically what it says, it'll make a pair of the elements from before the insertion point, the after the insertion point, and I must admit I never remember what stable partition does for more than a few minutes, because that's not my field of specialization, not my area, but people who write this kind of code of course get used to it, and you can look it up. So it is shorter, it is simpler, it is faster, it is usable in far many areas, and there's no loops and tests. Once you have convinced yourself that this is correct, it'll stay correct. It takes a little bit reading of manual as opposed to hacking code, and there's some people who strongly prefer to hack the code. But this is the kind of thing. So I'm trying to recommend that, to a large extent, move away from random code with loops and tests, and try and think in terms of algorithms and how to generalize things. This would be a culture change, because a lot of programmers are trained at hacking random code and is very proud of complicated control structures. But when I see complicated code, I get worried. And we know where bugs hide. One of the obvious places it hide is in big chunks of code, especially big chunks of code with a lot of loops and tests in it. The other way it can hide is an enormous number of function calls to get work done. But anyway, we try to simplify code and try to make it better documented as formal algorithms. And so, finally, to get any of this, we have to stay high level whenever we can. And I'm trying to encourage you to believe that you can stay high level more often than you think. High level there is 14,000 feet. It's taken from the top of Mauna Kea, looking at Mauna Loa. Anyway, so people are really convinced that low-level code is efficient. They actually think that low-level messy code is more or less definition of efficiency, and a lot of people don't even bother measuring, because they know that low-level is more efficient than high-level. This is complete rubbish, but people think that way. So I've been doing experiments with levels here. Here we have two examples, a fairly classical loop that sums the elements of a vector, and then the same using the for each algorithm with a lambda that represented. The second is definitely higher level for each, from the beginning to the end, increment the sum. And I find on several systems with several compilers, basically the code generated for those two cases are identical. It's you choose based on the style you like, not based on efficiency concerns. Now, for each, and this sum is a very simple algorithm, but if I was saying for breadth first search versus a depth first search, the one can be written like a simple loop, and the other one really is an algorithm. and you have to stick to the algorithms. So try to do the thing. That, of course, is accumulate, so you should just call the standard accumulate anyway. But this is just an example of code where you might think there was some overhead somewhere, and I couldn't find it, with several compilers and several systems. Here's another example that I've been doing for ages. This is qsort versus sort. Sort, of course, is cleaner, more general, and easier to use than qsort. And for that reason, widely believed that it has to be slower. It isn't. For examples like sorting any reasonable sized container, say, and I think this number was for 10,000 or 100,000 elements, sort was 2.5 times faster than qsort. For the reasons, better type safety used by the optimizers, better inlining, you don't have to have those indirect function calls. It's just cleaner and therefore runs much faster. So if you do performance of C-style and object-oriented code, it's roughly equal. But once you start using type-safe high-level code, you start getting performance advantages too. Sort being the standard example. Anything in the standard library, you can get performance just by using it. So low-level does not mean efficient. And don't lower your abstraction level before you absolutely know you have to. So this is a different version of the old saying that don't do premature optimization, or Jan Bentley's version, don't optimize yet. And you repeat that a few times. But stay high level as you can. Now, you may have noticed that I have not said anything about inheritance. This is partly because I assume you know everything about it, and I had to cut out something. Secondly, inheritance is wonderful if your application domain really is hierarchical. But people seem to be forcing all kinds of strange things into hierarchies, and having hierarchies just for the sake of hierarchies. I mean, you have a lot of programmers who think that object-oriented means never use a freestanding function. And that's just silly, because most of the things we do does not fit into hierarchies. And so another reason for not emphasizing inheritance here, apart from I assume you know it, is that it has been seriously overused for the last couple of decades. Object-oriented programming using hierarchies is a wonderful way of writing some code. It is an awful way of writing all code. And by the way, I could say that of just about any sort of general solution. It doesn't fit in all possible cases. We have to find a blend of things based on high level, type safety, and things like that. So I have to say a little bit about concurrency. There's many kinds of concurrency. C++ 11 supports type-safe, type-rich programming at the threads and locks level. I would like to be at a higher level of abstraction than threads and locks, but we have to do systems level work. We have to interact with the operating system, whatever it is, and that's the level where the operating system is. So this you can think of as a foundation on top of which you can build other things. And if that's too high level for you, you can also do lock-free programming on that. But anyway, I'm not going into details here. That's Hans Böhm's next talk. That's on the memory model and a little bit about concurrency, I believe. But here is how you can write threading in modern C++. I have a function, I have a function object, and then down there I make T1, which is the thread that will execute f on vec on vec1 on a separate thread. And we have T2 that will execute the function object initialized with vec2 on a separate thread. And of course, we then have to join the threads later, and we can start using the results. Very simple example. The point here is not that this is new. We've been writing code like this for 2-3 decades. The point is that we don't have to do any messing with void stars or anything else like this. We have gotten type safety and we've gotten standard things. This will work on all the systems. That's nice. And I'd like to just show that you can go a little bit further by parsing results. So here I make a thread T1 that calculates F1 and puts the result in the res, and we do it again and we join. So we get the standard function or the style, and we use lambdas to pass them along. And finally, we can simplify this even further by not talking about threads and locks and joins, but talking about tasks to be executed asynchronously. A task is just some work to be done. And here I'm saying I would asynchronously like F to be called on some vec. And I would like asynchronously G to be called on some vec. You may worry that I'm starting two asynchronous threads on the same vector, but it's const, and constant immutability is great in concurrent systems, so I'm not actually shooting myself in the foot. Now, async, which is a standard function, will return something that you can get the results from. That something is called a future, and basically a kind of a handle to the thread's result mechanism. And so get res1, get res2. Notice they're defined as auto, so I didn't have to be specific about it. Auto is the mechanism in C++ 11 that says pick your type from your initializer. So I didn't have to talk about futures here at all. I'm just saying asynchronously run F, asynchronously run G, get the results from the first computation, get the result from the second computation, and we're home. So that's much more elegant and often faster, because you would not really want to spawn more than one thread here. The other one could run on the original. So basically, here's a summary. Practice type-rich programming, as said. Integrate error handling and resource handling. Focus on compact data structures, and prefer algorithms to random code, and build and use libraries. A lot of what C++ is for is writing libraries so that you don't have to write on the raw language, just like we use the type system, so we don't have to write on the raw machine. And so the first stage in most problems is to build a library that supports your application domain, and you can do it with type-safe concurrency, and you have the standard library to get started with. I wish we had many more area-specific libraries that were standard, but we don't. At least there are some of them. And so here I can take questions. I think we have a system for taking questions, and I think we need microphones so that everybody can hear the questions. Yes. Is there somebody handing microphones around? Any questions? There's a question there.
Well, I have a question, but I don't have a microphone, but I don't think it will be necessary.
Oh.
You know, there's one thing, this is great talk to start with, but I do have one thing that I find unconvincing, and that was when you made this little description about the difference between using a list and a vector. That kind of, to me, we lose a little bit of abstraction when you start thinking like that. Because when you were picking the list versus the vector, you were really thinking about how that was implemented, even down to the issue of memory caching and stuff like that. So that, to me, kind of betrays, how should I say? It betrays maybe we want to design list and vector in a different way. Because when I think of list, I'm thinking of something that I attach to a lot, or I walk through, or I don't access randomly. And when I think vector, I'm thinking of something that I need access randomly, and I shouldn't really have to think about how it's implemented. I should be able to just presume that if I pick a list, it's the best implementation of that fundamental concept.
I think I understand what you're saying, and I think you happen to be wrong. What we should say is that we need a sequence of elements. And the default sequence of elements in C++ is a vector. Now, because that is compact and efficient, implementation mapping to hardware matters. Now, if you want to optimize for insertion and deletion, you say, well, I don't want the default version of a sequence. I want the specialized one, which is a list. And if you do that, you should know enough to say, I'm accepting some costs and some problems, like slow traversals and more memory usage. And I think too many people are not thinking at all about these things and writing bloatware. So think about vector as a default container of element, the default sequence, and you depart from that only when you try to optimize. Think about a linked list as a specialization, as an optimization. And we can't do that automatically for you. People have not figured out how to pick data structures optimally relative to their use in a program. And so we start with vector. We can go to lists sometimes. We go to map a lot. We go to unordered maps, hash tables a lot, or sets. But we have to have a reason for doing so. And I don't think I'm lowering the level of abstraction at all. So there's a question here, I think coming out of Twitter. It says, you've been writing move code for a decade. How did you go about doing it? Okay. There is a version that can be found on the web of my favorite solution. I wrote a course and a book for novices called Programming Practice and Principles and Practice using C++. And on my web pages, you can find a support page for that. And for the support page for that, there's some code. And in particular, there is a little matrix library that shows how to do it. The basic trick is that inside the matrix is a copy constructor and a bit that says whether you copy or move. And so if I say nothing, it's a move. If I say exfer, transfer, the next copy operation turns into a move. It's a hack. It works beautifully in the hands of a library implementer, and the users don't have to know about it. Anything that can be done can be done, and somebody has done it. But today, in C++ 11, you don't have to know that hack, and you don't have to do it. And the major compilers ship with move semantics in them, so it is not science fiction.
Question in the back.
There's one up there.
Thank you. Having a standard interface to your collection, such as an iterator, you can completely optimize later by determining at the declaration what type of collection, whether it's a vector or a list or a hash table or whatnot, and you don't have to change any code that is relying on the implementation of that. And then second of all, I have a question, which is to do with C++ 11. I've spent a lot of time in my career over the past 25 years writing protected data members with getters and setters for these, with the presumption that later, at some point, I'm going to change the logic and the rules about accessing those. I found that almost never I've had to use that, and I'm now starting to look at going back to having public data members. And I've also tried to come up with an abstraction to declare a property so that it has getters and setters that could be intercepted by the class that owns it. And I'm just wondering if any thought has been put to that with C++ 11, or if that is a problem that we can find an easier way for declaring properties in C++.
The notion of properties have cropped up again and again. I think that protected data is a pretty hopeless idea. It got in, sounded like a good idea, and it turned out not to be. So I prefer my data to either be public or private. I can manage those two things. properties with getters and setters that do things are very common in certain systems. I'm not sure that they should be, but they are. And you can write a library that does very nice property facilities. Nobody has made that standard. It was almost done for the previous standard, and rather little work has been done in the C++11 time frame for that. I don't know if that's going to crop up again. If it does, it'll take some time. So if that really is a major part of your programming life, and it is for some people, think about how to write a little property library where you have a property type that takes as a parameter the real type, and you can then start overriding the getter and setter mechanisms. It's half a page of code.
Yeah, so that's what I tried to implement. And I found, first of all, it's very difficult for the class that owns it.
I can't hear you. I can't hear you.
Oh, I'm sorry. I said, implementing that, I found there was really not
Wait for the mic.
for the parent class to actually intercept the get or set of that property, and that property abstraction basically got in the way many times because you had to explicitly use the get or set to get the actual type to see the members of the actual object. So would you recommend that we start to use public data and not worry about that, and occasionally change the code that accesses it when a rule comes into place?
I can't answer that without knowing the application domain. Similarly, some people have found the property library is sufficient. Others have found it insufficient. It seems to depend critically on what you are doing, and you should talk to people who know your application area better than I do.
Great. We got a question right back there.
There are joint strike fighter C++ coding guidelines, and you were part of developing those. And you made a comment that those did not include exceptions because tool did not have enough support to use exceptions in mission-critical applications. And that was in 2005, so I was just wondering if the tools finally caught up, and what were the problems that exceptions could not be used.
So what he's talking about is the guidelines for writing the flight control software for the next generation strike fighter, the F-35s. One thing that you have to take into account when you write software for that is that a small mistake in the code can lose you a very expensive plane and possibly a pilot. The rules were written with a safety officer sitting at the end of the table and every half hour piping up saying, "But is it safe?" Where safe is defined as somebody might die if it isn't. Now, this is sort of slightly ironic when you're talking about a fighter plane, but so the concern here is about reliability, but also performance. In particular, it is a hard real-time problem. So one of the rules for hard real-time is that every operation has to be predictable. And in C++, actually, every operation is predictable, with the exception of new and delete, so you can't use those, and throw and dynamic cast. We actually developed a constant time dynamic cast. I don't know if it's actually used. If you look at my publication record, we actually developed a fast dynamic cast. But getting back to the exceptions, if you throw an exception, you want a guarantee that it gets to a handler within a very small number of milliseconds. There's no guarantee in the language for that to happen. There's no guarantee that a throw from a given point comes from the same source, so it may take different times. This is not predictable, therefore it's not useful. It would become useful the minute you had a tool that analyzed all the throw path, to the handlers and gave you back a reliable upper bound on the time that you took to get there. That tool does not exist. I don't think the tool could exist in general for all code, however messy. I think you would hit the halting problem. But you could say, you could build a tool that gave you that bound or said it couldn't do it. In which case, if the bound was small enough, you'd be allowed to use exception handling, and your code would get cleaner and I think more reliable. But we don't have that tool today either. I had expected to have it today, but other things came in the way. I don't know if the airplane guys have it. I don't know.
All right, we got another question there.
So you talked about using stack allocation and just having objects be declared on the stack wherever possible, and that's something I try to do as much as I can. But it's not always clear that the stack has enough room for large objects. And in those situations, if I happen to be the unlucky stack frame right after a big allocation, I sometimes crash, and I find that there is no standard compliant way for me to deal with that. Do you know of this being a larger problem, and do you know if there is a good way to ensure that you don't run out of stack space?
There's no standard way of reporting that you've run out of stack. That's unfortunate. And it's a problem, especially in embedded systems where there's not as much stack as we might be used to. And the only thing I can recommend is not to put really large objects on the stack in large numbers. Because usually there is, these days, quite a lot of stack space. And you saw the objects I was dealing with, by and large, were handles. And a vector of 1,000,000 elements takes up 3 words on the stack, so that's not the problem. And that alleviates the problem in many areas. So I can't solve the general thing. It's something to do with the interaction with hardware in non-predictable ways for stack overflow, but use smaller objects and get them as handles. That's the only thing I can do.
So it seems that your slide about inheritance and how it's been overused and forcing objects into hierarchies that aren't necessarily really required. It seems to me that part of the reason that people do that is to build some sort of interface for that code that they can pass objects that would have those particular method calls. Obviously, one solution to that is to instead use the template system and to get the genericity involved in that. But as soon as you start throwing templates at people, some people get icky about that and decide that they would rather do the object-oriented inheritance. Is there any? Do you have any comments or suggestions about how to fix that?
Yeah, that slide is really a talk that's longer than this talk. Sometimes I noticed that I had an example up that said I didn't want an object to be my my base class, my interface, because that's a meaningless interface. But I suggest the shape might be a good interface abstraction, which is a base class. Furthermore, a widget might be another one. The graphics domain is ripe with useful abstractions that are hierarchical. And so that's fine. And you can even parameterize them. Things like vectors of shape pointers is a good example of where you get a mixture of generics and object-oriented code. I'm not saying everything should be templates. I just didn't have enough time to discuss where the trade-offs lie. Not everything should be a hierarchy. Not everything should be a template.
Great, got a question.
So C++ is becoming like a huge Swiss Army knife. Is there some thought being put into creating sort of like a strict mode which would be like a guideline for compilers to try to sort of forbid some obsolete features or features which could be dangerous, like protected or maybe friend, maybe go-to?
C++ is large, but it's not particularly larger than other languages people are using. It is really hard to deem, in general, what is dangerous or what is inefficient or what is useless or whatever criteria is. My impression is that everything that's in C++ is essential to some user community of maybe a couple of 100,000 people. And so take away anything major and you hurt a couple of 100,000 people. Well, basically you can't, because they'll just use it anyway and ignore you. Take away something minor and it's ridiculous because you don't have any effect. And whenever you take something minor, you still break some old code, and people really hate you breaking their code for any reason whatsoever, because it hurt them now. So there's been a lot of thoughts about subsetting C++. We don't really know how to do it, because some of the most dangerous features in terms of what you can do with them are essential for efficient implementation of the higher level abstractions that we really want. So a subset would have to tell the difference between an abstraction we like vector, and a feature we consider dangerous, like pointers into arrays, and accept the latter only behind the interfaces. This is quite hard. But sort of the first attempts to create a safe subset of C++ must be almost 30 years ago, long before it was called C++. And we again and again find that people's criteria for what they want and don't want vary dramatically, and it's context sensitive. The distinction between inside and outside an abstraction has to be part of the answer. And nobody has actually done something really useful for that. And what you get instead is coding guidelines and actually verifiers against coding guidelines that do know the difference between the set of abstractions for a particular domain. That you can do. But doing it in general, I don't know how to, because for any major feature, there's a community that relies on it.
Okay, we got time for one more question. You can pick out Jennifer. I'm sorry.
Oh.
You know what? There is a panel at the end of the day, so
Yeah.
keep your questions in your head, and
Yeah.
we'll geek out later.
Yeah, there's a way of asking questions at the end of today and at the end of tomorrow, and that may even be better because I won't be the only one answering the questions, and you may get more than one answer. Anyway, last question.
Is this thing on? Okay, yeah. My question's about move constructors.
Yep.
So first I want to say that they're definitely going to make our code faster. It's fantastic that they're added. But in our experience with programmers is they really are lazy and they don't like writing default constructors, copy constructors, operator equals. And now I'm seeing with move constructors like a 66% increase in things they're going to be lazy about. So do you have any suggestions or guidelines on, or maybe it should be like a compiler warning if a compiler can see something, on things we can do to improve that?
There's a set of rules for what defaults you get and don't get. And basically, if you don't write a destructor, you probably don't have any need for move and copy constructors. You get the defaults. That'll work. They don't have to do it. And I really think people should stick to the defaults rather than trying to write them themselves. If you want the default semantics, you should not write your own constructors, move or copy. If you want special semantics, yes, you want it and you do it. And there is ways of saying if you want to do, say, a copy constructor, you want the default, but the move constructor you want to write yourself, you can simply say the copy constructor equals default. You get the default and then write your own move constructor. So there's a set of defaults and a way of getting them by default and a way of saying you want the default that that addresses that problem. And I think it will at least be significantly improved, if not totally eliminated. And thank you.
Thank you.